A new video shows a human-shaped robot escaping from a miniature jail by transferring itself into a liquid metal state and then slipping through the prison cell bars. Very Terminator 2-esque. And how is that even possible? Researcher and mechanical engineer and co-author of the paper, Majidi of Carnegie Mellon University, breaks down his experiment and its possible real-life applications. Join us as we get rebelliously curious. Carmel, thank you for joining me on Rebelliously Curious today. So you are a mechanical engineer at Carnegie Mellon University, and you worked on this amazing, I would say, paper also that was attached to another university as well. And we'll get into that, but it almost has this like Terminator 2-esque feel to it. So anyone who's seen this, and obviously I will preface this video before even doing this interview, so everyone will see it. Can you explain to me what the premise of this experiment was in this research paper and this study that you did and how you got involved in it?
Sure. So the premise of this is to explore shape morphing matter. So these are materials that can rapidly and reversibly change their shape. And in this case, also change their stiffness. We derive inspiration mostly from natural organisms, marine organisms like the sea cucumber. But you mentioned the Terminator, right? And you know, there's plenty of examples in science fiction also of these kind of shape reconfigurable, shape morphing types of robots and machines. And quite frankly, I mean, that kind of also, you know, inspired this vision as well. So that's something that my group has been involved with for quite a while now, for well over 10 years. And there's research groups throughout the world. So not just my collaborators in China, but groups in plenty of countries looking at new paradigms and new approaches to building machines and robots that have these kind of shape morphing type properties.
What made you want to start this then? Like, what made you want to go, I want to create a shape-shifting robot or even just a type of metal? Like, what made you want to start something like that? Like, what really sparked that inspiration?
Right. Well, I've always been interested in nature and drawing lessons from nature to build machines and robotic systems. I mean, ever since, college, undergrad, I've been interested in understanding kind of human locomotion and natural organisms from the perspective of robotics and machinery, and really understanding why we as humans, move the way we move, and, why kind of our bodies are kind of, engineered the way they are, and really trying to draw inspiration from that and seeing if we could build machines and robots that could be a little bit more lifelike, and not just for assisting us and doing our kind of regular everyday tasks, but also kind of, building, machines that can just go out in the world and be more resilient and more adaptive, and behave in ways that are a little bit more autonomous and capable of a variety of different functions. And so, this idea of kind of drawing inspiration from nature, from biology, to build machines and robots, that's something that has certainly been central to the research I've done, but it's also something that a lot of other researchers, especially within robotics, they've been doing for quite a number of decades now. So that's kind of really where the origin is. A lot of this more recent work with looking at stiffness tuning and shape morphing and working with soft materials, these liquid metals, for example, that kind of represents the current kind of iteration of these biologically inspired machines and robotics. It kind of represents a trend called soft robotics. So I'm happy to talk more about that, but that's really kind of where this work is originating from.
Yeah, and I'd love to know a little bit more about what soft robotics would be and what that consists of.
So soft robotics is actually been around for a while. So I talk about it being kind of the current iteration or embodiment of biologically inspired machines and robots. But soft robots, bio-inspired robots, I mean, these concepts have been around pretty much as long as, robotics has been around as a field. I mean, what really kind of initiated and motivated robotics dating back over a century ago was this notion that we could build machines that could replicate humans and their ability to perform tasks. And even the name, even the word robot, translates, I believe in Hungarian, to something like, robot or, mechanical labor or something. So this kind of vision has been around for a long time. And almost since the inception of the field of robotics, engineers have looked at nature and they've tried to build motors and muscles and different types of robotic systems that use soft materials or use fluids and gases. And so a lot of these kind of concepts in terms of the materials that are used currently in soft robotics have also been around for a while. But it really wasn't until kind of the last 10 to 15 years that it really kind of started to accelerate and started to be revisited, by engineers who, for a long time, were really just looking at kind of more kind of hard case kind of robotic systems, motorized systems, and things that we kind of associate with more industrial automation and big kind of robots and industrial plants and factories, and thinking again, oh no, there's actually a lot that we can do if we just continue to look at using different types of materials. And so that's kind of what kind of revived this interest in soft robotics after all this time. And so that's kind of where we are right now with the work that I'm doing, a lot of my colleagues.
Can you explain too, because the video is pretty amazing. Can you explain, maybe not step by step, but what people are seeing? Because we have this like Lego action figure man that does this, very layman terms here, very not scientific when I'm going to explain this, but melts and then moves within these jail cell bars, and then it rebuilds itself. Can you explain that process and what that is and what people are seeing there?
Sure. So what you're seeing are different stages of this stiffness tuning and shape reconfigurable property of this material. So the material itself is a mixture of a low melting point metal called gallium. So this is a metal that has a melting point just a little bit above room temperature. So it's so low that if you even just put it on the palm of your hand, just your body heats enough to melt it, and so it'll turn into a liquid. In that gallium, we've mixed in magnetic microparticles, and the role of the microparticles is to make this substance responsive to magnetic fields. So if you take out a kitchen magnet or some kind of permanent magnet, or if you have an electromagnet, you can actually manipulate the material. You can get it to change shape. You can get it to move around. So what you're seeing in that video is, starting out, we've cast that gallium and magnetic, with that magnetic powder in it, into that Lego figurine. And it's in that enclosure, that kind of jail cell. What we next do is we apply an alternating magnetic field. So it's a magnetic field where the field is kind of changing in a way that it induces electrical current within the gallium. And so as that electrical current starts to form within the gallium, it heats the gallium up, past its melting point, it causes it to turn from a solid to a liquid. And then you see it kind of ooze down. We then apply a magnetic field to basically pull it, through the jail bars. And so now all that substance is outside of that enclosure. Now, what's not captured in the video, which is kind of the last step, is basically what we do is, and basically the video stops at this point, it's edited out. So the substance is removed, it's cast in a mold to basically restore that shape. It's cooled down, so the substance goes back from being liquid to solid. Then it's kind of placed, on the table outside of the jail cell. So it's a little bit, I mean, if you just saw the video alone, it wouldn't be really clear kind of all the different stages. In the journal paper, we kind of go through all the steps. So it is clear from there, but if you just saw the video in isolation, I mean, it doesn't kind of capture it all, but it captures most of those steps. And I still think it's a pretty exciting demonstration of what we can do with stiffness tuning and also this kind of magnetic manipulation.
It states in Christopher Plain's article that he wrote for the debrief that you've created a new material, and I believe it's called a magnoactive. Can you break that down for us and what that consists of?
Right. So overall, the substance, we call it a magnetoactive phase-changing material. And so this substance has kind of a unique combination of properties. Other groups, my lab actually included, have looked at using metals like gallium and there's other metal alloys that have very low melting point. And we've looked at ways of achieving stiffness tuning with those kind of metals. Separately, there's been a lot of work on these magnetically responsive materials. So if you add magnetic particles or ferromagnetic particles, materials even like, iron, for example, or iron oxide. If you put them into a soft substance in an oil or say a rubber, then you can basically make those materials responsive to magnetic field. This study was among the first, or actually, possibly the first that looked at kind of fusing these two types of material systems together. So you had a material that not only was magnetically responsive, but it also had this stiffness tuning property so that, when you apply this alternating magnetic field, suddenly you could get it to transition from being stiff and or solid to being kind of liquidy and easy to kind of deform and move around. And so it's both the magnetic activated, but also that phase changing kind of response. And that's kind of what is unique about this material system.
I saw another section too that was called extreme liquid. So it's extreme liquid phase. Can you break that down for people as well and what that means? Is that the moment that is like melting? Is that the extreme liquid phase and that we're seeing pushed through the gel bar cells?
Right. I mean, and we were, quite frankly, a little bit liberal with the language. I think, some of this was, there's definitely a lot of kind of scientific exploration of these material systems and a lot of, kind of rigorous characterization, but to kind of communicate, these concepts at a higher level, so my, colleagues in China and I, we kind of, used language, just to really emphasize, to beat people on the head, that these materials are quite different than what's been demonstrated in the past. So we say extreme liquid, really to capture the fact that these materials, when in their soft state, are very fluid. They have what's called very low viscosity. So water, for example, is a fluid that has very low viscosity. It flows very easily. You don't have to apply really much in terms of pressure or any kind of force to get it to move around. In contrast, a fluid that has very high viscosity would be something like peanut butter, right? Or a paste. Where you actually have to kind of push on it a little bit, right? Or kind of force it just to kind of ooze and flow around. And so we really wanted to make a distinction between materials that have low viscosity, say like water, and we were kind of targeting that in terms of the types of the kind of the fluidic nature that we were after. And that's something that's very different than what's been done in the past. In previous work with these phase changing materials or stiffness tuning materials, it would go from being rigid, being solid, to being paste-like, or being, somewhat rubbery and soft, but definitely not like, water-like in terms of its low viscosity. And so to make that clear, we kind of called it this like kind of extreme liquid-like behavior.
Then how does the Chinese University of Hong Kong play a part in this? Because I know that you did the study, you co-authored this with them, but how did they play a part in all of this?
So they actually really led this research. So the work itself was a collaboration between my lab, Chinese University of Hong Kong, and also Sun Yat-sen University. So my former PhD student, who is one of the lead researchers on this paper, his name is Chengfeng Pan. He was, at the time of this study, a postdoctoral researcher at Chinese University of Hong Kong. And the other collaborator was a group at Sun Yat-sen University. This is actually, the professor there was actually Chengfeng's master's thesis advisor. So I was the PhD advisor, Chengfeng included his master's thesis advisor, kind of brought all of us together. And the reason that he brought us together was that this research really built on a lot of the work that we've just kind of collectively done, my work on these low melting point metals, materials like gallium, and then the work that was done on these magnetically responsive materials. And so the research, a lot of the activities were done at Sun Yat-sen and Chinese University of Hong Kong. In passing, I'll note that Chengfeng did get a faculty position. So now he has his own research group at another university in China, Zhejiang University. But anyways, these are people who I've had wonderful working relationships with. We are continuing to collaborate. In fact, we have kind of another paper that we're currently working on. And so it's been a really fruitful collaboration.
Yeah, it's exciting. Now, when we look at this, because it's done in such a smaller form, how is this practical than a larger application? And where would we see this in larger applications as well in the future?
Right. So a big motivation of this, like I said, I mean, a lot of this work was inspired by natural organisms, marine organisms like the sea cucumber, which also has this, pretty extraordinary stiffness tuning property. Soft robotics generally as a field, I mean, is focused on these types of shape morphing and shape reconfigurable type systems. But another big driver for this work was to come up with new materials and machines that could be used for minimally invasive medical operations. And so my colleagues in China, they also do a lot of work looking at implantable devices or devices that can be placed in, say, the bloodstream or placed in the stomach and be used to perform certain medical operations. For those types of applications, you really don't want anything that's really big and bulky and rigid. You want things that are small, right? Or kind of soft and capable of changing their stiffness or shape so they can kind of move easily through these confined spaces. So that was kind of one thing that they were after. And the other thing that they were after is they wanted material systems and machines and robotics that could be remotely operated. So instead of having to come in with probes and, to kind of send electrical signals to these. They wanted to be able to access it over wireless magnetic field or electromagnetic field. And so that's something that really kind of was the driving force behind pursuing this research. And so as part of that, my colleagues actually, looked at using these kind of materials for drug delivery and also for removing foreign objects, say from the stomach. Now, they didn't do these tests on an actual human stomach or even an animal. Instead, they just did a kind of a toy model of a stomach. But, nonetheless, it shows kind of early steps. I mean, this is still very, still the nascent stages of this research. But it shows that these materials could potentially be useful for biomedical applications, and that's really what why this work is impactful. And again, I mean, the goal here is to manipulate really small volumes of material. The idea is not to have huge human size types of machines or robots that are that with these. I mean, that just wouldn't be practical for a lot of cases.
Yeah, I like the biomedical side of it because when I read that, I was like, I didn't even think of that. I was like, that is so interesting and so smart. Will there be a next step that we see within this research that goes into human testing at some point in time, or even just animal testing to start? I know some people are obviously animal advocates, won't always like that, but has that even just been a conversation that you guys have had?
It is, and it's something that my colleagues in China are currently pursuing. So they actually do studies with animal models, and that is the next step. And I should say more broadly, a lot of research groups that work on these magnetically responsive materials and soft robotic systems have been primarily focused on biomedical applications. So certainly doing those tests and doing that validation with animal models first before moving on to, say, studies with human subjects and clinical trials. I mean, that obviously is one direction. What I'm doing in my own group is actually to better understand the biocompatibility of the materials. And so really understanding if there's any concern about cytotoxicity, what happens when these materials come in direct contact with cells and biological tissue. To do those, we're not doing any tests on animals or any kind of humans. Instead, what we're doing is we're actually just growing using tissue engineering techniques. We're actually growing cells and tissue on these materials, and then kind of examining where basically what what the viability of cell growth and proliferation is. And so for those studies, we've specifically looked at gallium and these kind of gallium-based low melting point metals and alloys. And so what we found is that under certain circumstances, these materials actually are biocompatible. They are safe for contact with cells and tissue, but that's still something that's ongoing and something that we'll continue to explore.
Now, would we see that in regular practice? And this might be hard to obviously estimate, but when would that be possible to see that in actual practicality for humans to use and like biomedical research to use?
Realistically, I think there's a shorter path to seeing these used outside of the body. So maybe as a pad or a sticker that would go on the skin that would be used for some kind of diagnostics or even, therapy. Something that we worked a lot with are to blend liquid metal, so these gallium-based alloys, with rubbers and gels, and create basically electrodes that can stick to your skin and can be used to monitor all sorts of health vitals. So we can measure cardiac activity, muscle activity, even neural and brain activity. We can also use these to actually stimulate activity too. So we can actually pass voltage or electrical current, and we can do neuromuscular stimulation with these materials. So this is all outside of the body on the skin. And for that, there's kind of much more evidence that these materials are safe for contact. So practically speaking, I see that as being kind of the first examples of where these materials are going to be used. In a healthcare type scenario. Down the road, I still see that these materials could be viable for implants and applications in the body, or things like minimally invasive surgery or drug delivery. This is something that we're again exploring in terms of the biocompatibility of the materials, but a lot of other groups have looked at gallium and these gallium-based metal alloys, and I've actually found that there are kind of a lot of opportunities there. So that's something that's further down the road. I don't have a good sense at this stage in terms of what the timeline will be in terms of the basically all the regulatory steps. I actually have a spin-off company for my lab that has a product that's kind of currently going through FDA approval. And so I think with the right tests, with the right communication with regulatory agencies, I'm very optimistic, that there will be a pathway to get these out. And it's really just a matter of kind of finding what that clinical use case is going to be.
So after your studies come out, what has the comments been by your peers? What do they think? And has any other universities or anyone else in this field reached out to collaborate with you on this moving forward?
Right. So this paper has drawn a lot of attention, not just among, my colleagues in academia, but just, people, even in the mainstream. I mean, the kind of the public have also been really captivated by some of the findings from this work. I would say that, as far as how this is, influencing some of the work that's being done within academia, it definitely does represent just one more way that gallium, as a low melting point metal, really kind of can be used to introduce unique and really kind of exceptional properties in robots and machines in these engineered systems, properties that otherwise wouldn't be possible with just copper and silver or gold, or your conventional types of metals that are traditionally used in engineering and electronics. And so it just basically has kind of broadened, the range of different, applications and things that can be possible, with metals. And so for that reason, it has kind of inspired and attracted a lot of interest from my colleagues. Now, something that we definitely want to explore as next steps with these collaborations is to look at more versatile ways to print these materials. So use methods like 3D printing, additive manufacturing to better integrate these materials, create more complex 3D shapes. What we've done in this current study is just use kind of more traditional casting of materials. So we just cast them in molds. That's a manually labor-intensive type process. And so by using 3D printing out of manufacturing, we can kind of automate that manufacturing process and create much more complex structures. So that kind of is kind of how we would use a lot of these collaborations.
It's such a cool experiment, and the video is amazing too. So is there any misconceptions that you might want to clear up around the video along with then the research that you're doing?
Sure. I mean, things that I would clear about these material systems, definitely they can't really get scaled up to very large volumes. It works quite well at the millimeter and centimeter scale. So when you're talking about small systems that, size of like a capsule that you could kind of ingest in your, and then have it, go in your body, or something that could go in your bloodstream, right? For that, I think that's kind of more manageable and realistic in terms of what can be manipulated with magnetic fields that you could have kind of in a confined space. Anything kind of above and beyond that, something that's on the scale of a human, or even like, tens or, hundreds of cubic centimeters, then you're talking about needing, really large electromagnets and, things even bigger than an MRI machine. So, I would say that definitely is something that we're not by any means claiming, would be possible or even desirable. So that's, I would say, one. And the other thing is, going back to our discussion about the video, I think, does a nice job of kind of capturing, maybe 2 out of 3 steps, right? The transition from solid to liquid, the ability to manipulate the liquid and, get out, the jail bars, or through the jail bars and out of that confined space. But that last step is something that remains elusive. Right now, to restore the figurine shape, like I said, we have to cast it in a mold and re-solidify it. The dream is that, we would have the ability to basically get these materials to kind of restore their shape in a more automated way. So that's not going to be quite possible just with these materials alone. We're definitely going to have to do more. My group, through some other collaborations, have been looking at shape memory materials. There's all sorts of different materials, some of them quite exotic, that have the ability to remember their shape. And then they can spontaneously go back to that under the right conditions and stimulation. So that's something that still is a little bit far along, in terms of, incorporating that with these magnetically responsive phase-changing materials. But that would be something else that we're not there yet. So that could potentially be a misconception of somebody who just sees the video and say, oh, wow, these guys succeeded. And that's not quite the case. And then the third, of course, is the need to really understand the cytotoxicity and biocompatibility of these materials, to really determine if they can actually safely be used for these medical applications. So even though that's something that we, show promise for in the paper, there's still a lot more work that has to be done there.
So you're not telling me we're having Terminator 2? That's not going to happen. That's not possible yet.
Thankfully not. I'll be the first to say. Right. Yeah, I mean, this still requires a lot of manual intervention, I think, before you can get to something like that. But that's kind of where the field is headed.
Well, when you said, the day that it can actually rebuild itself, I was like, wow. And I'm glad that you cleared that up, because that was one thing I thought when I saw it. I'm like, oh my gosh, like this, it's actually rebuilding itself, which was unbelievable. But all of the work that you're doing is amazing. So we're excited to see what happens in the future. And Carmel, thank you so much today for joining me and for being rebelliously curious.
Thank you so much.